Suppose the previously written and shown program executes up to the point of call to the fork method, as it is marked by the red arrow. If the call to this fork is executed successfully, then Unix, or for that matter Linux, will do something like this. It'll create two identical copies of address spaces. One of the address space is for the parent process, while the other address space is for the child process. Both the processes will start their execution at the next statement that follows the fork system call. As is in this case, both the processes will start their execution at the assignment statement as shown. Both these processes start their execution right after the system call fork. Since both processes have identical but separate address spaces, those variables initialized before the fork call have the same values in both the address spaces. Since every process has its own address space, any modifications will be independent of the others. In other words, if the parent changes the value of its variable, the modifications will only affect the variable in the parent's process address space. Other address spaces created by the fork calls will not be affected even though they have identical variable names. Now, what is the reason of using write rather than printf? Because printf is buffered, which means printf will group the output of the process together. While buffering the output of a parent process, the child may also use printf to print out some information, which will also be buffered. As a result, since the output will not be sent to the screen immediately, you may not get the right order to the expected result. What worse, the output from the two processes may be mixed in strange ways. To overcome this problem, you may consider to use the unbuffered write system call. Let us consider one more example which distinguishes the parent from child. Here, once the call to the fork is done, the returned value is stored in a variable called PID, which is of type PID underscore T. Now, if the PID is equal to 0, then the function child process will get executed. And if the PID is not equal to 0, then the function parent process will get executed. In both the functions, child process and parent process, a loop will go for a maximum count, for which in the child process the child will print the value of I, and once the loop terminates it prints the child process is done. And the similar thing happens in the parent process. So when you compile and run the program, you should get an output where both the child and the parent process should print these values. Now the parent is printing the values. Now it is child. Again the parent and child mixed. Now it is over. In this program, both the processors print lines that indicate whether the line is printed by the child or by the parent process, and the value of the variable I. For simplicity though, the function printf is used. When the main program executes fork, an identical copy of its address space, including the program and all the data, is created. The system call fork returns the child's process ID in the parent, and it returns 0 in the child process. The following figure on your screen will show that in both the address spaces there is a variable called PID. The one in the parent receives the child's process ID, which say 3456 as in the explanation does, and the one in the child receives 0. Now both the programs will execute independent of each other starting at the next statement. In the parent though, since PID is not 0, it calls the function parent process. On the other hand, child has a 0 PID, thus it calls the function child process, as it will show on your screen. Due to the fact that the CPU scheduler will assign a time quanta for each process, the parent or the child process will run for some time before the control is switched to the other, and the running process will print some lines before you can see any line printed by the other process. which is exactly the reason why we put the maximum count value large enough so that both the processes run for at least two or more time quantums. Had we put the max count so small, then the process would have finished one time quantum, and you would have seen the two groups of lines, each of which contains all lines printed by the same program. The Linux system calls that transform